Right, okay, thank you for turning up to this, folks. I hope you enjoy it. What I'm going to talk about today is the problem of building a calendar for a planet other than Earth. In particular, I'm going to look at the problem of building a calendar for Mars, because we're already there. We have arrived on Mars. Timekeeping on Mars is not some vague theoretical thing nowadays. It's actually a practical engineering problem. So how are we going to approach it? Well, most timekeeping is really an exercise in practical astronomy. From the beginnings of humanity, we've been able to do timekeeping by looking at the things around us. And because timekeeping works with simple things like, is it light out there or is it dark out there? It is an astronomically based function. So our original timekeeping functions are things like the day, the rising and setting of the sun. The next timekeeping measure that early humanity probably noticed was the moon, because the moon has a regular 28-ish day cycle, and they can see it changing from day to day. There's also longer patterns, so you get to see the change in temperature. So temperature changes over the seasons, and this allows you to get the idea of the year. Now, the year was almost certainly first measured in terms of warm period to warm period. It wasn't actually initially defined astronomically, but it would have been one of the very early astronomical measures that was taken. Once people started observing the motions of the sun and the moon and the other stars, then they would be able to see all of these things. Okay, someone still has their mic turned on. I can hear noises. Sorry. Okay, so astronomically speaking, calendars are all astronomy. It's all space science stuff. Yay. So what time units do we actually deal with? Well, we have astronomical time units and we have cultural time units. And the earliest time units that we recognize are the Babylonian ones. So if we look at the astronomical units, we have the day, which is one rotation of the planet, 23 hours, 56 minutes. We can actually define several different forms of rotation, but don't worry about that. We've got the month, we've got the lunar phase cycle. We can see the moon changing from night to night. It is 29.53, but we've got a 27.3 day sidereal cycle. So when we're looking from same position to same position. The year is one solar orbit, 365.25 days. And these are the accurate timings. Now, we're not very good at dealing with accuracy as a culture. What we tend to do is to round things up. So we can then look at the cultural calendar. Now, cultural calendars are all based upon the astronomical stuff, but they round things up accordingly. So the first definitions come from the Babylonian, which 24-hour day, 12 hours and 12 hours. And this allowed them to say, well, okay, yes, it works. It gives us a workable period. Where do we get 24 from? Actually, nobody knows. No one knows why everything is set up into 12s, because the Babylonians had a really cool base 60 numerical system. And of course, 60 works well with 12, so you'll get 12 and 5. There is the argument that 12 is a better number than 10 for a numerical system, because it's divisible by 2 and 3 and 4 and 6 rather than just 2 and 5. So we don't know why it ended up as 24 hours, 12 and 12, but this is where the cultural side of calendar definition actually comes in. We then have the month, and again, the Babylonians defined a month as a 30-day period. Now, why take a month as being 30 days rather than just a visual lunar month? Well, this is because they have the year defined, and they defined the year. It was easier to define a calendar year than to define a calendar month. So they defined effectively a 59-day double month, which had a full month of 30 days, followed by a hollow month of 29 days. And all of this comes from cuneiform tablets. So we know that this was their calendric definition. Then their full year was 6 double months plus a few holidays. So, you know, you could have a few days holiday at the end of the year. Fantastic. Now, if we're going to base all of this on the astronomical processes, then we have to have waypoints within the sky. So we have to be able to define astronomical events that let us measure time from one event to another event. And the normal events that we use are the equinoxes and the solstices. And I see I've got a typo on this. Never mind. It's the summer solstice. So the spring equinox, normally round about the 21st of March, that is the start of the astronomical spring, and that's the point at which the Earth passes through the crossover point between the celestial equator and the plane of the ecliptic. 3 months later, we hit the summer equinox, and at that point, day and night on the equator are roughly even, or are even. The planet is at its highest point or lowest point, so the sun is at its highest point or lowest point in the sky. We hit 3 months later the autumnal equinox, and that's the start of autumn. And then 3 months after that, we're back, we hit the winter solstice, the sun is at the lowest point in the sky, and we can get back to the start of winter, and then the next one is the next spring equinox again. So we just go through this cycle, and all of it is based upon the position of the sun in the sky or the position of the Earth in its orbit. Now, I mentioned right at the start that planning for time on Mars is now actually a serious engineering problem. And this is because we are there. We are on Mars. Mars is the only planet currently known to be entirely populated by robots. We've had quite a lot of Mars exploration missions on. These are the main ones. We've actually had another couple come in since then. I must update this slide. Mars Reconnaissance Orbiter, Exploration Rovers, Express, Odyssey, Science Lab. You know, there's a lot of them out there nowadays. So timekeeping for Mars is a serious problem in the space community. We have to work out how to do this and how to do it in a way that everyone is using the same times. So this is quite important. Well, naturally, JPL came up with a solution. JPL, who control most of the Mars missions, have a wonderful working scheme. They don't actually use Earth time anymore. If you have a day shift working on one of the Mars rovers, then your day shift is Mars's day. It's not Earth day at all. They work on Mars time. So they have calibrated their work shifts not in days, but in sols, because the sol is the term that has become used for a day, a sunrise to sunrise period in for Mars or any other Martian day period. And this actually became an interesting problem for the people working on the Mars programs. So what they did, the watchmaker Garrow and Serlian built specialized watches for the JPL team, which have the Earth time on one side and Mars time on the other side. Now, these are not, they're not electronic watches. These are proper manual watches, but he's weighted everything slightly differently so that on Mars time, it gives you the extra half an hour, just less than half an hour. So these things are so cool, and I want one. I've also looked at how expensive they are, and I'm not going to get one. Fortunately, there are other alternatives. For instance, the Mars 24 sun clock. Now, this is what NASA uses, and if you go to www.gis.nasa.gov tools, you can download it. It requires Java, but it will tell you the time on Mars whenever you want. So the time on Mars is probably now. I'm going to move this around so I can see it. Yeah, it's probably, I said I'd start at 4, didn't I? Actually, we're about half an hour beyond, half an hour under that. I got my timing wrong when I set this up. But as you can see, it will work out what the Mars time is, and it will work it out not only for a location on Mars or on the equivalent of Greenwich, the 0 degree longitude. You can actually get it to tell you the time at any particular location, you know, a landmark or one of the research stations or one of the rovers. So it's quite a fun tool. For the rovers, it will give you a time in sols as well, which is how long since they landed. So it's quite a fun widget. So this is showing the map, and it will show you the different locations that you can see where everything is on the planet. So that one there is Olympus Mons, because I quite like Olympus Mons, but you can plot all of the different rovers and so forth, or positions on the planet, which is quite nice. So how do we do this? Well, how do the Mars rovers do it? I've just said that NASA and JPL work on Mars time, but one problem we've got is that in the same way that we have different time zones here on Earth, we have to have different time zones on Mars, because each of the landers uses its own local solar time. The reason for this is most of these things are solar powered. Well, in fact, I think they're all solar powered at this point. So you need to think of working from dawn to dusk. So you have to think in terms of local time. So what we have is coordinated Mars time, MTC, which is the equivalent of Greenwich Mean Time for Mars. So this is based on the meridian in the Airy Zero crater. So the meridian just goes straight through the middle of the crater, and that is its starting point. Now, the way this is then calculated for local time, or coordinated Mars time, is that it assumes that 1 Martian hour is 2.7% longer than an Earth hour. So similarly, a Martian minute is effectively 2.7% longer than an Earth minute. Now, this is probably the most practical way to work, because if we want to work with a 24-hour clock, then having 24 and a bit hours is not an ideal solution. We can have some alternatives, and indeed Kim Stanley Robinson took quite a lot of time to think about, well, how is he going to handle this for his Red Mars, Green Mars, Blue Mars series. And his approach was to say, okay, we're going to run everything on Earth time, but we're not going to click over to a new day until the full Martian day has completed. And as there's a 39.5 minute extra period, 2.7% of the day is effectively 39.5 minutes, you've got this dead time between the actual Martian local time and the Earth clock that has been imposed on the planet. Yes, it works in a novel. In practice, it's not going to work. We need to have something where we can measure in a straightforward, continuous way time moving on. It doesn't make any sense to have, it's currently the 4th of April, the 4th of April, the 4th of April, 4th of April, and dum-de-dum-de-dum-de-dum-de-dum, now it's the 5th of April. So in a practical sense, we need to have something that gives us the true local time. Have I clicked the right way? Yes. Okay. So how do we deal with this? Well, right now our mission clocks count in sols, so Martian days. When I originally wrote this, Opportunity was on Sol 3683 because Opportunity had been doing bloody well in terms of surviving as a mission. You know, those little Mars rovers do fantastically well. But we also need to give a seasonal date. So we want to have some sort of month date. Now, it's actually really tricky if we just calculate the day number. Today is the 4th of April, which means it is day 94 of 2020. I had no idea it was day 94 of 2020. I had to look that up. I knew it was April the 4th, but calling it day 94, no, I had to look that up. As humans, we are much happier dealing in smaller amounts. So this is one of the reasons why we define months and we define seasons. So we want to be able to do the same thing for Mars. Now, the way we do it is we look at the LS, which is the heliocentric longitude. In other words, whereabout on Mars's orbit is Mars today? And again, we're looking at the whole business of the vernal equinox is when the planet crosses the ecliptic. The solstices are when it is furthest away from the ecliptic. So in the same way that we can define those for the Earth, we can define those for Mars. They are straightforward astronomical measurements, and we define the vernal equinox is the starting point. The summer solstice is when Mars is a quarter of the way around its orbit. Another quarter of the way around, we reach the autumnal equinox. The winter solstice is another quarter of the way around, and then we get back to the beginning again. So this allows us to set up our sol date. Now, the sol date is defined as days elapsed since 12 noon on December the 29th, 1873. Yeah, what? Well, the reason they chose this date is because it was the time when they made the first major set of temporal measures of Mars. So they looked at Mars during the 1877 perihelic opposition, when it was furthest away from the sun, and Mars and Earth were both basically at the same points in their orbit. So it was lined up. It was lined up with the Earth. And they chose that as, okay, this is a good starting point for all of our measures. Why does it start at noon? Well, it starts at noon because the one true time starts at noon. The one true time is Greenwich Mean Astronomical Time. And all astronomical observations are measured on GMAT, because you really don't want to have to change the day in the middle of your observing run. So the calendar day would change at midnight, but that's a real pain if you're doing a long observing session from 11 o'clock till 3 o'clock in the morning, because you don't want to have to change your reference date. So therefore, Greenwich Mean Astronomical Time allows you to have the same observing day through a full night's observing session. This means that, of course, it's 12 hours out of sync with the calendar date, but you know, hey, we live with that. So this is very similar to the Julian date, which is what is used for Earth-based observations. But of course, the Julian date takes the same approach. It starts prior to astronomical observations on Earth. So again, it's way back pre-Babylonian. So this is how we measure the overall day. So suppose we want to do a set of calendar months. Okay, we're 30 years beyond now. We've got people landing and living on the moon. Yes, I know Elon Musk wants to do it a lot earlier than that, but I'm a bit of a realist. I'm a bit more realistic than perhaps he is. So we've arrived on Mars. We've built our first Mars base. How are we going to define a local time? Why are we going to define a local time? Well, we are Mars. We are not Earth. We are free. We are independent. We are not Earth. And it would just be silly to follow totally Earth time. So let's define our local Mars time. Okay, we've come from Earth. We're used to 24 hours. Let's stick with the whole 24-hour day. This is great. So the Sol, it's 24 Earth hours, 39.5 Earth minutes, but we're just going to define it as, great, that's 24 hours, no problem. 24 Martian hours. The year, no problem, obvious one, it is a solar orbit. How long does it take Mars to go round the sun? 668.6 sols, or 686.98 days. The fact that we've got a 0.6 in the sols mean that we're going to effectively have to have leap sols eventually. Our calendar is going to have to allow for the occasional leap sol. What about a month? How are we going to define months? Well, can we do it based on a moon? No, to be honest. Given that Phobos's orbital period is 7 hours 39 minutes and Deimos is only 30 hours 8 minutes, these are not particularly useful measures of time. So we're going to have to use something else. Now, fortunately, the Earth and the Moon are naked eye objects from Mars, which means that over the period of a month, we can see the positions of the Earth and the Moon get closer together, swap round, get to an extreme, come back again, swap over. In much the same way that we see the moons of Jupiter moving past the giant planet if we look at it in the sky for any period of time. So there's no reason why actually we can't use a month, the Earth-Moon standard month for this. So the sidereal lunar month would actually be a workable time unit. This is a picture from Mars, taken from Mars by the HiRISE mission, and it shows the Earth and the Moon. Yes, it has been processed to bring the colours out a bit, but this just shows that you can actually see the Earth and Moon as a paired system from Mars. So we can certainly set things up. How are we going to count these hours? We're going for our 24-ish hour. Well, unfortunately, the Martian North Celestial Pole is not particularly well marked. We've got a 6th magnitude star. The closest thing is Deneb. Deneb is a circumpolar star on Mars that would work reasonably effectively in the northern hemisphere for measuring relative time, in exactly the same way that we can measure relative time on Earth by looking at Ursa Major and working out which way it's pointing, because as it moves through the sky in the course of a night, we can actually tell time from it based upon where it is in the sky. And Canopus has the same function in the southern Martian hemisphere. So we can actually do I'm out on Mars, I'm standing on the surface, I can look up, I can find out what the time is at night in exactly the same way that we do it here on Earth, which is quite fun. If we're going to count the hours during the day, we've got a bit more trouble. The reason for this is that Mars's orbit is considerably more elliptical than Earth's is. So we can't use a sundial. On Earth, there is a difference between real time and sundial time of about 16.5 minutes. It's up to 16.5 minutes. The equation of time on Earth has lots of interesting wibbles and wobbles, but it never is further than 16.5 minutes away from clock time. Now, sundial time and clock time on Mars would be much, much further apart. It can be up to 50 minutes. And the result of this is that the analemma, so the position in the sky of the sun at 12 o'clock, 12 noon every day, draws out a teardrop rather than a figure of 8. The sun's analemma on Mars is a teardrop. So what each of these points on the diagram shows is every 10 sols, where in the sky is the sun? So it's definitely not the same shape as that on Earth. Okay, realistically speaking, it takes a lot of technology to go to Mars. It takes a lot of technology to stay alive on Mars. We're going to have electronic clocks. But knowing that you can do Mars dials, sundials on Mars, is still a cool thing. It's just they're not going to be very accurate. We can count the hours, that's fine. How do we count the days? Well, we've already said the year is roughly twice as long as it is on Earth. So how do we deal with this? Well, it's not only longer than the Earth year, it's also more, so the eccentricity is more, and the axial obliquity is not quite the same either. So what we end up with as a result of this is we have very uneven days and nights and very uneven seasons. Because the further out you move, the larger the difference between the speed of the planet's movement when it's close to the sun and the speed of the planet's movement when it's away from the sun. So we end up with, if you were to look at the Earth's calendar, we have roughly 90 days to a season. If you look at the Mars calendar, we've got anything from 142 days for autumn, right the way out to 193 days for spring. So this is an issue that's actually having a huge effect on Martian weather. So Martian weather, if you're going to terraform Mars, you have to allow for the fact that your seasons are a bit skew-if, and you're going to end up with the northern hemisphere has a short, warm winter and a long, cool summer, whereas the southern hemisphere has a very short, hot summer and a long, cold winter. So in practical terms then, if you're going to colonize Mars, go live in the northern hemisphere. The northern hemisphere has nowhere near the range of temperatures that the southern hemisphere has. So the northern hemisphere is much more hospitable. The seasons are also 90 degrees out of step with ours. So if you look at the blue circle, that shows you where the Earth's seasons lie, and VE is the vernal equinox. The vernal equinox, then 89 days, 90 days, 93, 93. If you look at Mars, the vernal equinox is actually quite a long way out. It has rotated up by 90 degrees, if you like. It's right there at the top. So if the Earth is just going into spring at that location in its orbit, Mars would just be going into winter for the same hemisphere. So this means that whereas the vernal equinox is the first point of Aries on Earth, it's going to be somewhere in Sagittarius for Mars. So that will affect your astronomy a little, but it also means that you are out of sync in terms of where the sun will be at the hottest times of the year, or the hottest and coldest times of the year. Now, I said before that counting the days is not good. Counting the longitude around the orbit is really not good, because that's worse than counting to 668. You know, that's counting to 360 with lots of fractions. So realistically, we can't define any Mars-based calendar periods that are medium length unless we start looking at the Earth Moon, and we use the Earth Moon visual reference point. So people started saying, well, okay, what can we do with a Mars calendar? How can we build this? And by 2000, over 70 different Martian calendars had been proposed. A lot of them had been proposed by science fiction authors. Others had been proposed by science geeks, astronomy geeks, and several had been proposed by the serious science, the serious space science community. And probably the most popular one is the Darien calendar, which was developed in 1985 by Thomas Gangel. And the Darien calendar is the one that more people are using, shall we say. And this says, okay, 24 months to the year. We'll keep the idea of the month because we can, after all, see the Earth Moon. And we've come from Earth, we're used to month as a time span. You then say we have 6 months to the season. Now, in some ways, this is going back to the old Babylonian concept of the double month. But now we're going to have 3 double months to a season rather than 3 single months to a season. So, you know, there's good cultural history behind these decisions. And what you do is you have 5 months of 28 sols, 1 month of 27 sol. And remember, I said that we were going to have leap sols. Well, the last month of the year will have 28 sols instead of 27 within a leap year. So that's going to be our leap sol. Now, when are we going to have leap years? Basically, odd numbered years. Odd numbered years, and also evenly numbered years that are divisible by 10 but not divisible by 100 unless they're divisible by 500. These are the jokers, these are the wild card years, in exactly the same way that 2000 should have been a leap year because it was divisible by 4, except it wasn't because it was divisible by 100. So even the Earth's leap year system is a bit screwed. So Mars's leap year system is going to have a fairly similar problem. Now, the Darien calendar has named months. So it has named the months for the zodiacal constellation of the month, which is quite nice. But because we've got 2 months where we'd have 1 month, we've got a second set of month names. And these are the Sanskrit constellation names. So the Indian ones, which are really quite cool, but would take a lot of learning, I suspect. And it would definitely be a thing that you have to learn. Kim Stanley Robinson uses the same approach in his Red, Green, Blue Mars series. He has 1st January and 2nd January. 1st February, 2nd February. Works quite well. I suspect that Robinson's idea would be more popular, mainly because we all know 12-month names, and it'll be a lot easier to put 1 January, 2 January, instead of 1 Sagittarius, 1 Danus. So I think that common use of the English language and the English language months, or no, the Western month identifiers are likely to hold. Because of the eccentricity of the orbit, though, we have a bit of a problem that the months don't really sync up well. Ideally, we'd like to be able to say the first of spring is going to appear at this point. Actually, here on Earth, if you look at the definitions of the seasons, the astronomical seasons are not the same as the meteorological seasons. The meteorological seasons are defined as starting the 1st of, I think it is March. I think December starts winter, March starts spring. But the astronomical ones, the winter solstice isn't until the 21st of December, and the spring equinox isn't until the 21st of March. So we're already slightly out of sync on Earth, but Mars would be even further so. What we have with the diagram is we're showing, well, okay, yes, if you start winter between Sagittarius and Vrishika, then all of these are going to be slightly out of sync because, as I said, the length of the seasons is not constant. We can have a 3-month season on Earth because it is basically 3 months because our orbit is nearly circular, but because Mars's orbit is much more stretched out, we have this problem where the seasons are uneven, so we can't just fit 3 double months into a season. So this is always going to be a bit of an issue. If we're living on Mars, is that a problem? I don't think it is, to be honest, because for most of the time we're going to be indoors anyway. You know, we're not going to terraform Mars quickly. So I suspect that sticking to the cultural calendar of Earth won't be a big issue. There's also the Zubrin calendar. Bob Zubrin of the Mars Society, one of the greatest voices for Mars that we have. He developed another calendar which is more astronomical than cultural, and he says, great, okay, we're going to say it takes us 1 month to go through 30 degrees of orbit, and we're going to name those months for the zodiacal constellations, and wherever Mars is, if you were looking from the sun, whichever constellation Mars is in, that's what the month is. Now, there is a certain astronomical logic to that I really appreciate. I quite like that. That's a solid thinking. Yes, the maths works. No one's going to accept it because people are going to get massively confused by how many days are in this month. We have enough trouble dealing with February. You know, the fact that we have little rhymes to tell us how many days of a month of each year, of each month in the year, shows that we're really not that good on dealing with uneven lengths of months. So I suspect that although scientifically this is a really cool thing, culturally people just wouldn't buy it, which is a bit sad, but you know, hey, culture does that. Okay, I can hear someone again, sorry. In 2006, there was a survey done, and yes, I am one of the people who answered the survey. And NASA basically said, well, okay, if we're going to have a calendar and a clock for Mars, how are we going to do it? Actually, no, I think it was the Mars Society, not NASA. And this is what people voted for. Now remember, most of the people voting for this are science fiction geeks and other space science geeks. But this was what people wanted: a 24-hour clock. 60 minutes per hour, 60 seconds per minute, and these hours and seconds and minutes will all be 2.75% longer than the terrestrial counterparts. We want 7-day weeks. We want equal duration months, 24 of them, 28 days each. We can have a 668 day non-leap year and a 669 day leap year. We can deal with the leap year pattern of odd numbered years plus decennial years, leap day at the end of the years, and a perpetual calendar that allows you to have an integral number of weeks per month. In effect, what people voted for was getting rid of all this stupid Roman emperor business of nicking days from one month to give to another month because they're important. So going back to a basic 28-day month was viewed as being the most practical approach. The perpetual calendar approach means that you always know that April the 4th is going to be a Saturday. If we've got a leap day, then we're not going to call it April the 29th. We're going to call it Leap Day. It may be technically April 29th, but it would probably be known as Leap Day. So it would not be a standard day of the week. In effect, a leap day would be a holiday. The idea that they like, begin the Martian calendar now rather than wait for a future event. So don't wait till someone lands on Mars to define the calendar. Let's have it up and running. And then let's increment the numerical year on the Martian cycle. So we've got the start point in 1876. Let's run the calendar from there for now. For now is because later on, no doubt, they will want to change it from the founding of the first city of Mars. It's just what they're going to do. But if we've got a working calendar, it still makes life a lot easier. And we'll begin the calendar year on the northern hemispheric vernal equinox. So we're still tied to an astronomical event, which is quite nice. So, predictions. The first manned mission will use Earth time, just because it will be reporting back to Earth, because it will be scientific, military, and it will use Earth time. Now, if we get into colonization, then we'll switch over to Mars time. And when the switch comes over will depend on who's doing it, whether it's military or civil. Because I suspect the scientific bases will switch earlier than military bases, just because the military won't want to run 2 time zones on 2 different planets. The scientists will be more open to this. If you run 2 time zones on 2 different planets, you are setting yourself up for mistranslations. Scientific and civilian groups, no problem. I suspect that they are likely to switch over. What we will see is Mars local time is used, but I don't think any of the created Mars calendars will be used will be in popular use for some time yet. In practice, what do I think we will end up with? A 24-hour sol, and I doubt we'll keep Monday, Tuesday, Wednesday, Thursday. I think we'll get something like 1 sol, 2 sol, 3 sol, 4 sol, up to 7 sol. The reason for this is compatible with Chinese day names. And the Chinese are doing so much work in space nowadays that it wouldn't surprise me for the first landing on Mars to have a significant Chinese component to it. 24 months, number them, or at worst 1 January, 2 January, but again, we may just have them numbered. Chinese approach. So if we've got 24 months, we'll take the Chinese approach. If we have 12 months, I suspect we would maintain the current names, so we end up with things like the 42nd of August. And we would define the year as landing based. So the first point we land on Mars, that will be year 0. And then we'll go from there. So I think that that would be a practical calendar for the future. There's a whole bunch of background reading you can do from this. Yeah, I'm afraid these are all journal-y type things, but you know, what do you expect from me? The Gangel and Dudley Rowley, 2006, The Social Construction of Time for Mars, Results of a Martian Time Survey, is the one that did the whole online survey. And it shows you what different groups of people are interested in, to be honest. Okay, so that covers everything. All of the slides for this are available there. In the short term, you can either grab a screenshot now or grab a screenshot at the end of the, if you watch the video again, or I will put the link back on Facebook